So the next topic we're going to discuss will be another sequential container. We've talked about vector now, and you're getting a chance to implement a vector-like class called ArrayList. And now we're going to talk about another sequential container known as deque. And deque is short for double-ended queue. And it's a data structure that allows efficient insertion and removal both at the end, like vector, as well as at the beginning. So you can think of this data structure as something that lets you put things efficiently at the end, take them efficiently off the end, and then also put them efficiently at the beginning and take them off efficiently at the beginning. You can insert elements in the middle, but it'll be less efficient because it has to move things around and stretch stuff out. And if you remove stuff, it has to collapse it and so on and so forth. So it's very efficient for adding things at the beginning or the end. And the way this works is it has methods called push front and pop front, which are kind of the front equivalents of push back and pop back, which we have for vector. And of course, it also has methods like in place back and in place front, which are optimized in various ways, as we've talked about before. We're not going to talk a lot about that right now, but that's a very cool thing to remind yourself about if you have parameters used for deque that are complicated and have complex constructors. So speaking about how you define a deque, so a deque is very much like a vector. It's got pretty much the same type signature. It's parameterized by type name t, which will be a deque of t, and it can also be allocated. It can also have an allocator, which defaults to the allocator that comes out of the box that uses operator new and delete, but you can take control of the memory allocation if you need to. And then there are situations where it's helpful to be able to control where the memory comes from. For example, you may have special kind of memory like battery-backed RAM in some embedded system, or you might want to have something that allocates its memory out of shared memory, and so on. But for now, we'll just stick with the out-of-the-box allocator. So I'm going to show you a whole bunch of examples. This is just kind of the segue into that, and you can find all the examples we're about to look at the link in my GitHub account at the bottom of the page. So let's go ahead and zip down here to into my CLion project, and I'll start by giving you kind of a deeper overview of what a deque is. So a deque is this double-ended queue that grows and shrinks at both ends efficiently, and they also, like vectors, support the sequential model. So the way that the elements end up in the deque is based on how they're added, either pushed at the end or pushed at the front, and they don't ever depend on the contents of the values, unlike, for example, the various ordered associative containers where they use the values as keys and ways of being able to order things in a red-black tree, a balanced red-black tree. The containers have the following properties. You can access their elements by the index position, and there's both range-checked and non-range-checked ways of doing that, much like with vector, much like with your array list assignment. You can iterate over the elements in any order. It's got so-called random access iterators, so you don't have to go from beginning to end or end to the beginning. You can go in whatever order makes sense to you. And again, as we said before, you can add things to the front and to the back efficiently. Okay, so as you can imagine, internally, to get this behavior of being able to add things efficiently to the front, the data structure has to be more sophisticated than what you have with a vector. A vector is just a big chunk of memory that's allocated contiguously and grows only at the end, whereas a deque has to be something that can grow at the beginning and at the end. And so as a result, it's typically not implemented, or it's not implemented contiguously. It's implemented in chunks. And so as a consequence, accessing any element in a deque while still constant time will not be quite as efficient as accessing any element in a vector. And likewise, when you destroy a deque, depending on how big it is, it may take longer to destroy because its destructor is going to have to go and free up all of the chunks that it uses internally to implement the semantics of the deque. Whereas with a vector, all its destructor has to do is just delete the contiguous buffer in one fell swoop, and as a consequence, it's much faster to free the memory up. So deque will be a little bit slower in a number of different ways than vector, but not wildly slower. The other thing to remember is that if you need deque semantics to put things at the front, then use a deque. If you don't need those semantics, stick with a vector. Always choose the STL container, be it sequential container or associative container or whatnot, that fulfills your purposes most efficiently while still meeting the semantics of what you're trying to do. All right, we talked about the interface, and you'll see that many of the same methods that are in vector are also in deque, but there's a few differences. For example, there's no capacity and no reserve method on a deque because we're not trying to optimize it by allocating all the memory simultaneously the way you could do that with a vector. And then, of course, there are these new methods added to push things at the front. And there's also this in place front method that we talked about earlier as well. So let's take a look at how you could use a deque. So this implementation is very, very simple, just showing you the bare bones capabilities. We make a deque of floats, and then we iterate through that from I equals 0, I less than 7. So we're going to push 0 through 6, and we're going to go ahead and push an element at the front and push an element at the back. And this should end up with sort of a palindrome-like output result, which we then print by using our good friend, the range-based for loop, to implicitly iterate over every element in the deque and print out its contents. So let's go ahead and run this code. As you can see here, as I mentioned before, it gives you a palindrome-like output where we have 6.6 at the beginning, 6.6 at the end, and then 5.5 at the next point, 5.5 at the next point from the end, and so on until we get to the beginning, which was 0. So that's showing us a deque. And I guess if I was really being appropriate here, I should probably not use I probably should use F, because of course it's not a deque of ints, it's a deque of floats, but it doesn't really matter, just for documentation purposes. Okay, so that's showing us one variant of deque, and you can see it's a very simple data structure. All right, now let's go ahead. It's really funny. For some reason, CLion periodically loses track of where you left off before. And so in that case, you have to kind of go searching from top to bottom through your directory hierarchy to find out where you want to keep going. CLion's reasonably cool, and it's free for academic use, but it's also can be a little quirky. Okay, as you can see now, we've opened up the next example. This is going to show us some other properties of deque. But before we do this, we're going to compare and contrast deque with vector. So when you have a large number of pushback calls for vector, use vector reserve. So what that says is make the thing be big enough so it doesn't have to keep reallocating the memory. Conversely, there is no reserve for deque, as we've talked about. As I mentioned before, if you have to remove a lot of items or if you have to shut down a large deque, it'll take longer to reclaim all the memory because it's allocating its internal data structure in terms of many chunks that have to be freed up individually, as opposed to in one single, one fell swoop with vector, where it removes it in one fell swoop. Typically, using insert or pop front with a deque will be more efficient than with a vector, and that's because it's optimized to put things at the beginning, whereas a vector is not. You have to shove everything down if you want to put something at the beginning. And as always, the fact that the deque is not implemented contiguously means that its at or subscript operations will be just a little bit slower than the ones for vector. Probably not wildly slower, certainly not orders of magnitude slower, but the constant factor will be somewhat higher because it has to do a little bit more work to go find the item it's looking for. So here's an example that uses random access iterators with a deque, and this is kind of a fun example. We're going to go ahead and push the letters A, B, C, D, E. So we're going to go through from 0 to less than 5, and we're going to push the capital letters A through E. And that's because we're using some funky magic here with adding the value 0 to the capital letter A returns the capital letter A. Adding the value 1, the capital letter A returns the capital letter B, and so on and so forth. So after we've done that, we go ahead and we print out the contents. And I guess if I'm really trying to be more intuitive here, I should say auto C, not auto I, because this will come out as a character. And then what we're going to do is we're going to go ahead and access various elements in our deque randomly. And you can see what we do is we say a deque begin, which gives us back a random access iterator. We'll talk more about those later. And that goes ahead and adds 2 to it. So that jumps to the 3rd location in the deque. And we store that as an iterator. So we have an deque iterator, deque of care iterator. And then just for kicks, we do the same thing, except this time we're going to go beginning of the deque plus 3. And now we're going to assign it as an auto iterator. So it kind of depends on your sensibility and your aesthetics. Old school STL programmers might prefer this approach because it's more clear what this thing is. It's an iterator. Modern school STL developers, myself included, kind of like the auto version because it's easy to tell. It's easier to type, and you know it's an iterator. You don't really care the details. Every iterator works exactly the same, and so there's no sense in having to type extra stuff. It just induces carpal tunnel syndrome. We then go ahead and write the results out by indirecting or dereferencing those iterators to get what they point to. And then we go ahead and we insert a value at the location for iterator 1. So we go ahead and we slip that thing in there. We'll go see where that puts the result in a second. Then we go ahead and print the contents again, which will once again, I should probably say C because it should be characters as opposed to ints. Not that it makes any difference, of course, in terms of the behavior of the program, whether I call it C or I, but it just makes more sense. Now, this is an interesting situation. So what we do after we insert an element is we go ahead and we reuse those iterators. And you're kind of walking on thin ice for sequential containers like deque and vector as to whether an iterator will still have a meaningful value after the underlying container has been modified. So you can see here we modified the underlying container. So this modifies the deque. Now, in this case, we might get lucky, and we may still have the iterators pointing to sensible locations and everything works fine. Conversely, our program could crash or could give you crazy results. And it all depends on whether or not inserting that element caused the deque's internal data structure to be modified. For vectors and deques, there's no guarantee that iterators into a vector or deque will retain any sensible values after the container is modified. Conversely, for containers like lists and sets and maps that use pointers internally as opposed to reasonably contiguous chunks of memory or completely contiguous chunks of memory in the case of a vector, those typically are not going to be affected if something is added or removed, unless, of course, you remove the item that you then have an iterator to, in which case all bets are off. It's probably going to crash or give you the wrong result. Okay, so let's go ahead and run this code and see what we get. Whoops, what we get here is a build failure. See if we can make that problem go away. Yep. So let's go ahead and run this code, and you can see here what happens. The original sequence that we printed out up here is basically A through E, all caps, as we saw. And then down here, you can see that we indexed into the beginning iterator plus 2, which actually skips to the 3rd element. So that'll be C, because everything starts at 0 in C++. And then we go ahead and assign it 2 to begin plus 3, which gets us D. And then we take it 1, which originally pointed to C, and we go ahead and insert an element. And so it modifies the deque by putting X before the iterator. So it puts it before the element that we were pointing to. So it was pointing to C, and now it goes ahead and shoves everything down by 1 and sticks X where C had been before. So that's the way that insert works with iterators on a deque. And it would also work the same way, of course, with a vector. And then when we're done, we go ahead and print out these iterators, and you can see that it1 now points to X, and it2 now points to C. So before, it2 had pointed to D, and now it points to C because it slid everything down. Again, you are on very thin ice if you write this code and expect it to do anything coherent. But in this particular case, because of the implementation details of deque and the fact that we didn't trigger a reallocation of the underlying chunks, we're okay. But that's risky. Okay, let's go ahead and talk about the next example. So this example is going to illustrate how to print the contents of a deck using a const iterator. And this comes back to a discussion we've had earlier today and on our Piazza discussion forum about what's the meaning of const and why is that important. So the good news is that this example will be a very concrete way for me to discuss the issues of const correctness, especially as it refers to const references and parameter passing in C++. And you'll see that the cool part about this is that the iterator mechanisms that are in C++ understand constness as well. And we'll look at a couple different variants here. Okay, so let's take a look here. And we have a print method. This is a generic print method that works on decks. It doesn't work on all containers, but it works on decks. It would be absolutely trivial to parameterize this to work on all containers, by the way, but we're not going to do that at the moment. And so what we're going to do here is we're going to take a const deque ref. And we're doing this for a couple reasons. First of all, we're trying to factor out the code for printing a deck so we don't have to keep rewriting it everywhere we need it. So that's number one. And that's why it's passing in a parameter to deck. And then the question arises, well, how do we pass that parameter? And we could pass it by value. We could say this. But of course, as you've seen in earlier discussions and earlier lessons, whenever you pass something by value, unless you go to the trouble of doing the move semantic stuff, which is quite overkill in this case, you'll end up making a deep copy. And we sure as heck don't want to make a deep copy of a deck parameter just to print its contents. That completely misses the point, especially if it's a large deck, especially if it's a full deck. And so, of course, we want to pass this by reference. And we want to pass it by const reference because the point is to print it, not to modify it. So if we just passed it as a deck reference, that would also work from a point of view of keeping it optimized. However, the problem would be that the caller or the callee, the method that's called, the print method, could accidentally modify the deck. And we sure as heck don't want that to happen. That would be a horrible mistake. So we're going to pass this as a const ref. So const in this purpose, in this context, is serving to document the intent that we're just doing this for optimization purposes, and we don't expect that the print method should have the rights to modify anything. Okay, so down here we then go ahead and print the number of items in the deck, deck d.size, and then we're going to go ahead and show the magic of const iterators. So were we to try to write this code, then this would cause the compiler to complain. What would the compiler complain about? Well, it would say, you're trying to treat this const deck, this const ref deck, as a non-const deck, and then you're trying to get a non-const iterator to it. And if you were able to get a non-const iterator to it, then you'd be in a position to modify the contents of the deck. And you're not supposed to do that because you passed it as const. Now, we can do all kinds of sleazy things like casting away const, and don't even get started with that. That would be a nightmare, bad idea. So the right thing to do in this case is to just say, all right, it's a const deck, so let's use a const iterator. And as you probably recall from our earlier discussions about this topic, a const iterator has a dereference operation that can only be used on the right-hand side of an assignment, or it can only be used to read the contents. You can't use it on the left-hand side. We can't have code here like this that would say something like star iter equal, I don't know, 10 or something like that. That wouldn't even work because it's a generic type. But let's assume it was int. It'll complain and say, hey, what are you trying to do? You're trying to use the dereference operation on the left-hand side of an assignment. This is const. You can't do that. I guess to be more abstract here, let's just say that. So this is going to be illegal for good reason. We don't want to be able to modify the contents of const. So that's kind of one thing. That's an example of how to use const. Now, I think you'll also agree that this is rather verbose. Look at this. We have to say type name space deck t : const iterator. That's a bit of a mouthful. So of course the compiler says use auto, And what it'll do there is it'll go ahead and make ourselves a const iterator using auto. So despite the fact we don't say const, it still is a const. And I think if we were really being conscientious to make the code's intent a little bit more clear, we would use C begin and C end. And C begin, as the name may imply, just says, I'm returning a const iterator. And that just is a little bit more clear. So let me go ahead and put this back here, what it was before. Type name, deque, const iterator. All right, so that's all good. And again, if we use C begin, it'll still complain even if we don't use C begin. But if we use C begin, it's really clear that we want a const iterator. So whether or not we use auto or whether or not we use const iterator, I think using C begin is probably the right thing to do here. Okay, so that's how we're going to print things. Hopefully that also explains a bit more about how const works and why const is so important to document the intent of the code, as well as to then allow the compiler to enforce the intent that you're documenting. Down here, we just use a couple of methods just for kicks. We go ahead and make an empty deque. We push 3 at the end, and we push 1 at the beginning. And then we're going to go ahead and we're going to insert it before a deque sub 1. So we're going to put 2 before a deque sub 1. A deque sub 1, of course, would have the value of 3 at the moment, because a deque sub 0 would have the value of 1. So if you insert something, it always goes before the iterator that you're putting in there. And this, of course, is just showing that we can use random access in order to do this. And then we're going to go ahead and assign the second location 0. So when we print the result, it should say 1, 2, 0. So when we print our deque, let's see if I'm telling you the truth. And yes, indeed, my compiler skills remain sharp as ever, and so it prints out 1, 2, and 0. Okay, let's now go ahead and talk about the last deque example. So this example will use 2 deques of characters, and it's going to go ahead and add a bunch of elements to both deques. It'll add basically the capital letters A through Z, and it'll also add the digits 0 through 9, all those characters. And then it'll go ahead and do some funky stuff with swap, and we'll see how swap works here. Remember, swap is a very important method that's used primarily for the purposes of exception safety, but you can use it for other purposes as well. So we go ahead and make ourselves 2 deques, first deque and next deque. Probably should call it second deque. Tell you what, let's do that. Let's call it my first deque, and then let's go in here and we'll call it my second deque. There's a really cool feature in that's in C Lion and other JetBrains IDEs, and actually other IDEs in general, like Eclipse and so on, that allow you to do wholesale replacement of symbols, which I just did here. So we're going to go ahead and push A through Z capital letters into the first deque, and then we're going to go ahead and push 0 through 9 as characters into the second deque. We're then going to print out the sizes of the deques, and we're going to print out the contents of the deques, and then we're going to go ahead and swap the deques. And after we swap them, of course, everything should be moved around. So the contents of the first deque will be in the second deque, and the contents of the second deque will be in the first deque. And then we print those results as well. So let's show what happens when we go ahead and actually run the code. And you can see here that we print out the first deque and the second deque. First deque is 26 characters long. The second deque is 10. We print the contents, then we swap things. And of course, after we swap them, the values have been swapped. So that works very nicely.